Investigate the basic features that should be provided in the DSP architecture to be used to implement the following nth order FIR filter, where YFN is equal to summation of I equal to 0 to n minus 1 h of I x of n minus I, where n is equal to 0, 1, 2 and so on, where x of n denotes the input sample, y of n output sample, h of I the ith filter coefficient, then x of n minus 1 is the input sample, I sample earlier than the x of n, that means previous input sample. Okay, here solution, here we can list out what are the features needed. The FI filter requires the following basic features for implementing this equation, YFN is equal to this equation. Here first one, memory for storage of signal samples, x of n minus 1. See here, if I value changes, what will happen? The x of n minus 1, x of n minus 2, this x of n value will be changes. For that, already we know that on-chip memory is for signal samples, that means RAM, write down here, RAM. Memory for storage of filter coefficients, already we know the h of 0, h of 1, so those are filter coefficients. For that we use ROM. Okay, a hardware multiplier and an adder to carry out the multiply and accumulate. Okay, here the multiplication, right? Multiplication and addition. For that, we use the MAC unit, multiplier and accumulate unit. Then a register to keep track of accumulation, that is we use accumulator. Then a signal pointer to point the signal sample in the memory. A signal pointer to point the signal sample in the memory. Then a coefficient pointer to point the filter coefficients in the memory. Okay, for the inputs, signal pointer. For filter coefficient, we use the coefficient pointer. Then a counter register to keep count of the MAC operations. Okay, then last one is capability to scale the signal value x of n as it is read from the memory, and the computed signal y of n as it is stored in the memory. For that, here we can do the scaling. For scaling purpose, we use the shifters. Shifters at the input side and output side. Just remember here. Okay. Then here we'll discuss about the DSP computational building blocks. One here, hardware building blocks that carry out the basic DSP computation. While choosing these building blocks, keep in mind the requirements of speed and accuracy, which are the two key issues in the design of DSP system. While choosing the DSP building blocks, okay, there are two key issues. What are those? One is speed and accuracy. Speed and accuracy. Okay, these building blocks could be configured to implement many different applications. Okay, such building blocks are configured to implement many different applications. Okay, here following are the basic building blocks that are essentially to carry out DSP computation. Okay, what are those computational building blocks? One is multiplier, shifter, MAC unit and ALU. Multiplier, shifter, MAC unit and ALU. Okay, here the multiplier. The advent of single chip multiplier and their integration into the microprocessor architecture are the most important reasons for the availability of commercial VLSI chips capable of implementing DSP functions. Okay, the multiplier is available as a chip. Okay, these multipliers called parallel or array multipliers. Okay, implement complete multiplication of two binary numbers to generate the product in a single processor cycle. Okay, the multiplication is one of the key operations in implementing DSP functions. Multiplication is one of the key operations in implementing DSP functions. The key features to be considered for a multipliers are already we know that. What are the key issues? One is accuracy, speed, and dynamic range. Here we already know that what is meant by in the previous class we discussed dynamic range. It depends on number of bits. Okay. Here the number of bits used to represent the multiplication operand and whether they are represented in fixed point or floating point format decide the accuracy and dynamic range of the multiplier. Already we know that dynamic range already we calculated, and also accuracy. The number of bits used to represent multiplication operands and whether they are represented in floating point or it's in fixed point format. Okay, which decide the accuracy and dynamic range. Whereas speed is decided by the architecture employed. Speed is decided by the architecture employed. Okay, if the multipliers are implemented using hardware, the speed of execution will be very high, but the circuit complexity will also increases considerably. Circuit complexity will also increases considerably. Okay, here if we wanted to increase the speed of execution, what will happen? The circuit complexity also increases. That's why here there is a trade-off between the speed of execution and the circuit complexity. Hence, the choice of architecture normally depends on the application. Here, parallel multiplier. Consider the multiplication of two unsigned numbers A and B. Let A be represented using m bits. Okay, A be represented using m bits. A of n minus A naught A1, A of n minus 2, A up to A of m minus 1. And B are represented using n bits as B of n minus 1, B of n minus 2 up to B naught. The multiplicand A, the multiplier B. The product is P. Okay, 4 cross 4 multiplication here consider A naught A1, A2, A3, B naught B1, B2, B3. See here, this is the partial product terms. P naught, P1, P2, P3, P4, P5, P6 and P7. Here the product have a maximum of m plus n bits. Each bit of product P is obtained by a summation of bits Ai Bj using an array of single bit adder. See here, this product term Ai Bj. Here we will get a partial product term by adding this Ai Bj. See here, the bits Ai Bj where the index I takes an on value from 0 to m minus 1 and Bj the index j from 0 to n minus 1 are formed using AND gates. The above figure shows the multiplication operation using 4 bits for both A and B. This one. You have to go through this. Okay. The hardware structure of multiplier for above example shown in figure 2. Here which requires 3 inputs, 2 output adders. It can be shown that for an n cross n multiplier, the number of adders required is, just remember, n into n minus 1. n into n minus 1. Here if you consider A is equal to summation of I equal to 0 to m minus 1 ai 2 raised to I, and B is equal to j equal to B equal to summation of j equal to 0 to n minus 1 bj 2 raised to j. Here this is the multiplication. P equal to summation of j equal to 0 to n minus 1, summation of I equal to 0 to m minus 1, this is 0. ai bj 2 raised to I plus. Here consider if m equal to n equal to 4, then we can perform the a is I equal to 0 to 3, summation of this one ai 2 raised to 2 raised to I, summation of j equal to 0 to 3 bj 2 raised to j, raised to j, expand this summation and expand this summation. Okay, then here now we get this is the p value product term. Okay, here p naught is a naught b naught, p1 is a naught b1 a1 b naught, p2 is this term, p3 this one, p4 this one, this is p5, this is p6, and last one is p7 2 raised to 7. This is the multiplier for signed number structure that is based on this equation, this simplification. Please go through this. If you simplify this one, you will get this one. Here p naught, what is there? A naught b naught, p naught, see here, a naught b naught, direct line, there is no addition. Then a naught b1 a1 b naught, a1 b naught, a naught b1. Here you can write like a naught b naught, a1 b naught, a2 b naught, a3 b naught. Okay, can keep in this row, keep b naught same. Okay, just you can add a naught a1 a2 a3. Similarly here one shift a naught b1 a1 b1 a2 b1 a3 b1. Similarly b2 here b2 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 a naught a1 a2 a3. Here you can add the plus sign. Okay, then we will get this structure. Okay, this is the P7 is carry from this operation. Okay, please practice this one. It's very, very important. The structure. The structure is called as Braun multiplier. The structure is called as Braun multiplier. The multiplier shown in this one is known as Braun multiplier. Yes, several improvements on this basic structure are possible and have been used to increase the speed and reduce the hardware complexity, and also one more parameter is added here, that is power dissipation. We can also reduce the hardware complexity and power dissipation, and also we can increase the speed. Okay, we consider one modification of the Braun structure which is essential to carry out multiplication of signed numbers. Okay, Braun multiplier does not take into account the signs of the numbers that are being multiplied. Additional hardware is required before and after the multiplication when signed numbers represented in 2's complement form are used. It would be described to have a structure that can directly operate on 2's complement numbers. 2's complement numbers. Okay, this is unsigned number multiplication. Here we are doing the signed number multiplications. Okay, during the signed number multiplication, what we can do? We can convert the given operands into 2's complement. Then we can perform the multiplication on those 2's complement numbers. Consider two numbers A and B represented in 2's complement. Let A have m bits and B have n bits. Okay, then A and B can be written as follows here. This is the 2's complement form of A, and this is the 2's complement form of B. Okay, let's go through this equation, product equation. Okay, this one. Here there are two subtractions in this equation. Can be expressed as additional of 2's complement numbers. The equation 7 can be modified to an expression with only additions and no subtraction, and can then be implemented through a structure called Bog-Woolley multiplier. Bog-Woolley multiplier. Here there is no subtraction. We can implement this equation number 7 using the addition only. Then we call it as Bog-Woolley multiplier. Here, speed. The shift and add technique requires n cycles for n cross n multiply. Okay. The cycle time is time to access the operands, perform add and shift, and store the result in the product register. That is called as cycle time. Okay. The parallel multiplier is a fully combinational implementation, and once the operands are available, the multiplication time is the longest path delay time through the gates and adders. We have to go through some parameters here. Okay, cycle time and the multiplication time. Okay, it is desirable to have multiplication time comparable to processing time of other computational units and access time of memory. As memory technology advances, lower and lower access times are achieved. Okay, high speed multiplier is achieved through parallel implementation. Okay, then the bus width. Consider the multiplication of two n-bit numbers x and y and the product z. If x and y are represented with n bits, and z can have a maximum of 2n bits. Maximum of 2n bits. Let us assume that both x and y are in memory and product z has also to be written back to the memory. Okay. In order to perform the whole operation in a single execution cycle, we require two buses of width n bits, each to fetch the operands x and y, and a bus of width 2n bits to store the result z to the memory. Although this performs the operation faster, it is not an efficient way of implementation as it is expensive. Here we are using to fetch the input, to access the input x and y, and also to store the outputs. Okay, we used here separate buses. The bus number will be increases. That's why the cost also increases. That's why it becomes expensive. Many alternatives for the above method have been proposed. Okay, one such method is to use the program bus itself to fetch one of the operands after fetching the instruction, thus requiring only one bus to fetch the operands, and the result z can be stored back to the memory using the same operand bus. But the problem with this is the result z is 2n bits long, whereas operand bus is just n bits long. Okay, see here, through the program bus we fetch the inputs and outputs using same data bus. Okay, using same bus we can also fetch the z. The z means its product, but actually here z is 2n bit. Then how we can fetch it? Okay, see here, we have two alternatives to solve this problem. One is use the n bits operand bus and save z at two successive memory locations. Use the n bit operand bus and save z at two successive memory locations, although it stores the exact value of z in the memory. It takes 2 cycles to store the result. Okay, first you can fetch the lower n bits then we can fetch the higher n bits. But here 2 cycles are required to store the result. And one more possibility is discard the lower n bits of the result Z and store only the higher order n bits into the memory. It is not applicable for the application where accurate result is required. Where the accurate result is required, then discarding the lower n bits is not possible. Okay. Then another alternative can be used for the application where speed is not a major concern, in which latches are used for input and outputs, thus requiring a single bus to fetch the operands and to store the result shown below. Here this is X and this is Y. Only single bus we use here. Okay, through this single bus we send the inputs X and Y of n bits. Then using this single n bits data bus we send the first n bits, then again some n bits. Like that we can transfer the